Thanks. So I should possibly also say, as an organiser, that if anyone wants to come for dinner afterwards in Nijmegen, we'll be going somewhere kind of probably sort of quick and simple, I think. So stay around, hang around afterwards if you're interested in coming for dinner with us. Okay. Yeah, so I think on the website it says that I'm going to talk about tropical geometry, and this is probably a little bit of an overstatement. I'm really not going to say anything about tropical geometry in general. I'm really going to talk about tropical curves and kind of how they appear as embedded tropical curves and how they appear as abstract tropical curves. So, I mean, if any of you have ever read like an introductory survey to tropical geometry, then you've probably seen pictures of embedded tropical curves as these kind of like certain sorts of graphs in R2. So it might look kind of something, I don't know, something a bit like this. Except I've probably drawn one that doesn't actually work. Anyway.
Yeah.
So that one works now at least. Okay. So kind of you think of these as inside R2 and these going all the way off to infinity. But somehow if you look in the paper that we're going to be studying, this is kind of not what a tropical curve is at all, really. Right? If you look at the definition of the paper we're studying, a tropical curve is some kind of abstract graph plus a load of edge lengths which take values in some commutative monoid, M. So basically what I want to do today is explain two things. First of all, where these kind of embedded tropical curves like this come from. And secondly, how do we go from this sort of embedded tropical curve to a more abstract tropical curve as we see in the paper. So, how to go from A to B. So I'm going to start with kind of seeing where they come from via tropicalization of algebraic varieties, in particular plane curves. Okay, so the general setup is we're going to take K, an algebraically closed field. Sorry, I've already said it's algebraically closed, I should say it's a field. And we're going to fix a non-Archimedean norm on K. So somehow the being algebraically closed is just a convenience. We'll see why in a minute. You can make it work in general, but kind of this is the key part here. So kind of the first example that springs to mind depends on whether you're a number theorist or an algebraic geometer. If you're a number theorist, then probably the first example that springs to mind is QP bar. If you're an algebraic geometer, then the first example is probably the field of Puiseux series, so the algebraic closure of the Laurent series field. So those are somehow the two canonical examples to keep in your head. And now, if I have such a field, I can look at the tropicalization map, which takes the k points of some torus, which is just k star to the n, and maps it to Rn. And what it does is it just sends some tuple of non-zero elements of k to the tuple given by the logarithm of their norms. And somehow the point is k algebraically closed means that this map is going to be dense, have dense image. So that's kind of what I've assumed this. And then what you can do is if you take some subscheme inside this torus, you can find the tropicalization of X to be just the closure of the image of X under this tropicalization map here. So I take phi of the k point of X, and I take the closure. And somehow the idea is that this tropicalization kind of sees some topological properties about kind of X and how it degenerates. This is sort of the general idea. So just to give a simple example, we can look at the pair of pants inside GM squared. So if I look at the vanishing locus of X plus Y plus 1 inside GM squared, this is isomorphic to P1 minus 3 points. And so this is kind of, over the complexes at least, it's sort of drawn in this way. Like this. And we can ask what its tropicalization is. So if we think about it, if we have X plus Y plus 1 equals 0, then what actually has to happen is that the maximum of the norms of these three terms has to occur at least twice. Right, and the reason for this is essentially the non-Archimedean triangle inequality. Right, is that if this max occurred uniquely, then this max would be the norm of this left-hand side. And somehow this can't happen because then we'd have a non-zero element of norm zero, a non-zero element of norm zero. So what this tells us is that the tropicalization of, if this is X, then tropicalization has to be contained in the set of all xy such that, sorry, this is really bad, but I want to keep x and y for coordinates on Rn. I want to use z and w for coordinates on Gm. Sorry about this. Apologies, everyone. So tropicalization, it has to be contained in the set of elements such that kind of max x, y, 0 occurs at least twice, just by taking the logarithm of this here. And we can draw this, well, if as soon as one of x and y is positive, they both have to be positive and they both have to be equal, so I get some segment like this. And otherwise, one of them always has to be equal to 0. So I get something like this. So the tropicalization has to be contained in this sort of thing. And actually, again, using the fact that it's algebraically closed, it's kind of not too hard to see that because of this operation of taking the closure, I'm actually going to end up with the whole thing. So it actually equals this thing.
Okay, I'm confused by this, because can't I always take the trivial norm where it's in everything non-zero to 1? Yes. So.
Okay, yeah, sorry, yeah, I should, like, this should be a non-discrete. Sorry, yeah, non-discrete norm.
Okay.
Right.
Some
yeah.
extra condition.
Yeah. It should have, like, after taking logs, it should have, like, dense image, I think, is, like, essentially the point. And kind of, I think the idea at this point is that somehow you're actually seeing some sort of shadow of the topology appearing in this picture. I myself don't know how seriously to take this point of view, but I get the impression that actually it should be taken quite seriously.
It's a dual graph.
Pardon?
It's a dual graph, so
yeah. Okay. And somehow, at least if we stick to plane curves, somehow, like, this example tells us, like, what the tropicalization looks like in general, in a way. At least it gives us kind of a formula for the tropicalization. So if I take x to be some plane curve inside GM squared, then the tropicalization of x is going to be exactly the set of points x, y, where, like, the maximum of the norms of the terms in this sum occurs at least twice, for exactly the same reasons. So I'm going to write this out carefully. it's the locus where max overall ij of log norm bij plus ix plus jy occurs at least twice, and the argument is the same as in this case. So just to draw another picture, although I won't kind of explain exactly where the picture comes from, that would take a little bit too long. So if you take an elliptic curve, so kind of the intersection of an elliptic curve with Gn, then the sort of picture that you can end up getting looks something like this. Yeah, where kind of all of these are going off towards infinity. And again, I think somehow like you are supposed to take this quite seriously, because like genus 1 is somehow reflecting the fact that you've got a loop here in the graph.
And the number of branches is the same as the number
It's of missing points. Yeah.
and there are actually natural bijection.
I don't know. I don't know. So like not every elliptic curve looks like this, but like this is the sort of example that you can get appearing. Okay. And kind of trying to describe exactly what we get when we do this process of tropicalization leads to the notion of an embedded, or at least a tropical curve, or at least an embedded plane. Tropical curve. So the idea of what's going on here is somehow when we take this map of logarithm of the norm, what we're doing is we're replacing the operations of multiplication in our original field by addition in the real numbers R, and we're replacing our original operation of addition in our field by maximum of any two real numbers. And so there's quite a convenient way of kind of capturing what's going on here, which is to introduce the tropical semi-ring. So as a set, this is just the real numbers union a point at minus infinity. And then we define operations by saying x kind of tropical plus y is equal to the maximum of x and y, and x tropical times y is just the normal sum of x and y. So this is a semi-ring in the sense that we don't necessarily have additive inverses anymore. But apart from that, the axioms still hold. And so now if we take some just formal polynomial expression with real coefficients, then we can use this to define a kind of like tropical function. So if I call this polynomial f, we get a tropical function f on R squared, where kind of I just stick in these sort of like different operations into this polynomial. So it sends x and y to the maximum overall ij of aij plus ix plus jy.
The log of the absolute value of aij?
No, because this is a real number, so I've already done log norm. Yes, this will be a little bit clearer in a minute, I think. Okay, so if these are our kind of like, and these are like the tropical version of polynomials, in a way. And so if these are polynomials, we should be able to talk about their kind of like, the tropical curves that they define. And somehow your first like naive guess would be to say, well, it should be the locus where this is 0. This turns out to be the wrong thing to do. And somehow the clue of the right thing to do exactly comes from here. Right, so in general we define the kind of the tropical curve associated to this tropical polynomial to be the set of points x, y, such that this function f is such that the maximum, this maximum occurs at least twice. So another way of seeing it is that somehow like there's going to be various pieces on which this maximum function is just like an affine function is just linear, and then we're looking at somehow the corner points of the function. We're looking at the points where the function is not smooth, so where it transitions from one piece to another.
So it is equivalent with saying it's those points where f is non-smooth?
Yes. Yeah. Okay, so now if we took our original, so if we took some polynomial g now over our original field k, so the coefficients now are bij, so these are elements of k here, then we can associate to it the tropical polynomial, where we just consider kind of the same thing, but we take log norm of the bij, and we replace kind of z by x and w by y. And then we've kind of set things up in such a way.
But you still have Bij, right?
Log bij, yes, sorry. Sorry, yeah. And then we've set things up in such a way that the tropicalization of the zero locus of G is the tropical curve defined by the tropicalization of G. And so now, like an embedded or at least an embedded plane tropical curve is just something of the form Vf for some tropical polynomial f. So just the things that we get by doing this sort of procedure. And these are the things that look like the pictures that you might have all seen before. Sorry, there's a
So this
question.
is something that always confuses me with tropical geometry.
Yeah.
So I feel bad to ask, but is the data of the tropical plane curve just the subset of R2, or should I remember the R? Or it seems very unclear. In
This is a good question.
Okay.
I don't have a good answer to this question. Like I get the from what I'm about to say, I get the impression that it is just the subset of R2.
Okay.
Because I think that's what makes what I'm about to say make that what I'm about to say will work if you just remember it as a subset of R2. So this is my feeling, but I'm not confident about this.
So there's no notion of isomorphism of such things or anything? It's really embedded. Oh, well,
No,
maybe
not
later.
yet. Yeah, not yet.
Yeah.
Okay. So I'm going to draw one more of these pictures. So let me get this right. So for example, if f is the following tropical polynomial, so then this is going to correspond to the function, well, it's going to be the max of 3x plus 2, y plus 2, x plus y plus 3, 2x, 2y, and kind of when you draw the corresponding tropical curve, the thing you end up with looks like this. And it looks something like this. So these are the sorts of pictures you're getting. Yeah, and at the moment these are just like graphs inside R2. Right. But like as kind of you're kind of all asking, we don't really necessarily just want to see these as certain subsets in R2, right? We want to see if there's any kind of way of considering them as some sort of abstract geometric objects in their own right, so that it makes sense to talk about isomorphisms or whatever between these things, and you know, to see whether they have some kind of abstract properties that don't necessarily depend on like how we've embedded them inside R squared. And at least a natural way to do this is to view these kind of embedded tropical curves as metric graphs, and that's what I'm going to talk about next. Okay, and so like the inspiration for at least the explanation I'm about to give kind of comes from algebraic geometry. So, you know, these are somehow the analogues of plane curves in algebraic geometry. And if we want to think about how we should view plane curves abstractly, then somehow the key thing to look at is what the regular functions on a plane curve are. And if we understand its ring of regular functions, then we sort of understand it as an abstract geometric object. And we're going to try to do the same thing here. We're going to try to see what the sort of allowable functions on these tropical curves are from the perspective of tropical geometry. And this is going to tell us how we should abstract them to get kind of curves without reference to any kind of embedding. And, well, I've rubbed it off the board, but we've kind of already seen the answer of what the allowable functions should be, right? Because these tropical curves were defined by, like, or were defined using these sorts of funny max functions for tropical polynomials. And so, again, if we're thinking by analogy of what happens for plane curves, then the allowable functions should be the restriction of these sorts of functions to our tropical curve. Right, and so if we kind of think about what sort of functions these are giving, these are exactly going to be piecewise linear functions with integer slopes. So our notion of good functions on tropical curves should be piecewise linear functions with integer slopes. And so now we can ask ourselves, kind of what structure do we need on these curves in order to make sense of this properly? Okay, so what we're going to do is we're going to kind of decorate our tropical curves a little bit in order to make sense of this side in a kind of completely combinatorial way. Yeah.
I'm pretty really stupid, but it seems like functions of that form will be less general. Won't there be somehow concave, convex?
Ah, yes. Sorry, you're right. This is going to be.
I mean, that feels something like ampleness or something. So we should just probably forget it for the abstract curves. But
yes.
I mean, I agree with you that we have the right notion of good function as piecewise linear with integer slope, but there's something slightly.
Yes.
More.
Yes. Yeah. There is. You're right. There is something slightly missing here. That these are going to be convex functions. Yeah. Sorry.
No. It's a motivating analysis.
Okay. So, like, if we take, let's take this one, right, and imagine that we've got some. Let's better not call it f. Let's call it h, like some piecewise linear function on this. Right. What I'm going to do is decorate it in a suitable way, so I should describe h by combinatorial data. So, I'm going to add a load of vertices. First of all, as just all the obvious vertices on the graph itself. I'm then going to add in a bunch of somehow vertices at infinity, so at the end of all these infinite branches. Okay, so these are the two kinds of vertices, And now I'm going to add a third kind of vertex coming, well, it's really going to be the same as this kind of vertex, but anyway. I'm also going to add vertices coming from the corner points of my function h. So h is going to be a piecewise linear function. There's going to be points at which I have like a break in the slope. And so I'm going to add in a whole bunch of other vertices, say here, 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 which come from the corner points of f. So they're the locus where f is not linear in a neighborhood.
H.
Sorry, h. Yes. Where h is not linear in a neighborhood of these points. Right. And so now I've got the situation where h is going to be linear on every edge of this graph. Right. That's how I've chosen these vertices. So if I know the length of edges, then then to specify h corresponds to specifying its value on vertices, first of all, and also specifying its slope on edges.
The values on the solid vertices.
Yes, sorry, for solid vertices. I don't have a value at the infinite vertices. So in other words, kind of the structure that I need to make sense of piecewise linear functions is going to be a graph together with lengths of edges. Right? That's what I need. And this is what like a metric graph is. So I'm not going to give somehow the obvious definition that you'd first write down. I'm going to give a slightly different definition and then explain why it's necessary, or why it is like it is. So a metric graph, gamma, is an oriented graph, G, consisting of vertices and oriented edges, together with some extra data. So the first bit of data is the vertices should be divided into finite vertices and infinite vertices. So a decomposition of V into finite and infinite vertices. A real number or infinity, so a positive real number or infinity for all edges. So in other words, I have a length of every edge, every oriented edge. I should emphasize this. And then finally, the bit that doesn't really make sense is an involution of the set of edges. Okay, so somehow what's going on here? Right, if you kind of first thought about a metric graph, you just write down an unoriented graph and the length of the edges. But somehow what's going on here is it's going to make bookkeeping slightly easier if instead, for every single unoriented edge, we put in 2 oriented edges going in opposite directions. It makes drawing the pictures a little bit uglier, but it makes talking about linear and piecewise linear functions a little bit easier. So kind of this is what's going on here. Right, and there are some axioms that this should satisfy. So such that. So first of all, the length of any edge is equal to the length of the kind of oppositely oriented edge going in the other direction. First of all, so secondly, that an edge has infinite length if and only if it meets an infinite vertex, so any edge between finite vertices has finite length. And then thirdly, any infinite vertex meets precisely one pair of oppositely oriented edges. So in other words, these are always like leaves of the graph. Like,
Am I allowed to have an edge between two infinite vertices?
an edge between two. Oh, sorry, yeah, yeah. I haven't quite covered that.
I think you are.
No, you are.
No.
It just goes all the way across.
Yeah. So yeah, I haven't excluded an edge between two infinite vertices.
But I think we want it later.
But it's why is that not allowed? Why would you?
So actually, yeah, no. In the multiple wise paper, it is eventually allowed, isn't it?
Yeah, and it's GM basically.
Yeah.
So
Yeah.
it's-
Yeah.
But maybe you want the graph to be connected. So it's not so.
So I think, I mean, I don't think we necessarily need the graph to be connected at this point. Somehow these definitions we're never going to use. I'm going to eventually write down a definition that we will really use, and that will be in the paper, and that will be correct. I'm just trying to motivate getting to that definition. Okay, so kind of the way we might think about what this sort of thing looks like is if we took our original pair of pants, right, which we're drawing like this, but now suppose we've subdivided it by putting a vertex here, and this segment has some length L, say, then kind of the metric graph we draw out of this, it has two finite vertices that we write with filled circles, a pair of opposite edges of length L, it has three infinite vertices, and then a pair of, then three pairs of opposite edges, all of infinite length. So yeah, like I said, this sort of thing of adding in more edges makes the pictures uglier, but it does make the definitions a little bit cleaner. Okay, and now this is exactly the amount of data that we need to say what it means to be piecewise linear, a function to be, or to define a piecewise linear function. So if gamma is a metric graph, so a piecewise linear function on gamma is a pair of functions. So what do I need? I need a function specifying its value on finite vertices, and I need a function specifying the slope on each oriented edge. And somehow this is why having oriented edges is nice, because somehow if I want to, if you want to specify the slope along an edge, you need an orientation, right? Because you need to know which way along the edge you're going. So it's a pair of functions like this, and there should be some compatibilities, right? So so the first is that the slope going one way is minus the slope going the other way. And somehow if you have an edge E from V to W, then the value at W is the value at V plus the length of the edge times the slope. In fact, actually, probably this implies this one, doesn't it? I'm now thinking. Yeah, okay, so I probably didn't need the first one, but... okay, so this is a piecewise linear function, and then we say that it's linear by definition if and only if I take any vertex and I sum over all edges leaving that vertex, and I sum all of the slopes of all of these edges, I get 0. So there's some kind of balancing condition at the at all the vertices.
I think you still need the first one for infinite vertices.
Ah, yes, you're right. Yes, thank you. Okay, so these are kind of like our first step at what an abstract tropical curve should be. It's one of these metrized graphs, or metric graph, sorry. Right, and there's one basic operation that we can do on them, which is subdivision. So kind of geometrically the way this works is very simple, is if we have some edge E of length L between, let's say, V and W, and I have kind of L1 plus L2 equals L, then I can kind of stick a vertex in the middle, and I can declare the lengths of the two edges I've created to be L1 and L2 respectively. So out of this I can kind of form a new metrized graph where somehow this one has length L1 and this one has length L2. This also works if one or the other is equal to infinity. So this is kind of like the basic operation. So I could also allow a kind of an infinite vertex here. Okay, and so the point is that we can produce these metric graphs out of the tropical curves that we had earlier. So if I have some plane tropical curve, then I can produce out of it a metric graph by kind of giving the lengths of the edges just like the lengths they have in Euclidean 2 space, right? And now if I have, again let's call it H, a piecewise linear function on X, then after subdivision I get a piecewise linear function on gamma. So I get a piecewise linear function on some subdivision of gamma. And so this is somehow the reason that, like, so some authors say that an abstract tropical curve is an equivalence class of metric graphs for the relation generated by subdivision. This is not the definition that appears in the paper, and it's not the one we're going to use, unfortunately. So in the paper, kind of what happens is that it's actually slightly more convenient to regard subdivided metric graphs as different, because somehow they correspond to something nice happening on the geometric side of things that you want to remember. So we won't use this definition of an abstract tropical curve as an equivalence class up to subdivision, but this is one that is sometimes used. Okay.
So can you say something about this notion of being linear? How does it relate to functions on the curve or to?
Yeah. So for these tropical curves, it will mean that it's linear in the kind of sense that you'd imagine for this graph inside R2.
Okay.
It will correspond to the same thing. Actually, so no, I should be careful. I don't think that's actually true. There's possibly an issue coming from like weighting of edges. So I haven't put weights on any of my edges, but this is something that does occur occasionally. Like sometimes you want to do this, and I think that possibly has a relevance for the linearity condition. So yeah, I probably shouldn't say this corresponds to being linear in the previous sense, but yeah.
Like if the sum of the outgoing vertices, the sum of the outgoing edges was 0 somehow, then this would correspond to linearity, but that's not necessarily, a priori it's not necessarily the case.
Yeah, yeah.
But I think it is actually the case, but this is a theorem. But then maybe the weights.
Yeah, I'm not sure of what the precise statement should be about how to compare the two. Sorry. So, again, this is not quite the way that these abstract tropical curves appear in the paper. They make somehow one more level of abstraction. So it's that level now that I'm going to talk about. And so the basic idea is that if we have a metric graph gamma, then the edge lengths by definition are either a positive real number or infinity, and this process of subdividing edges is kind of a reflection of addition here. And kind of what they do in the paper, I think, well, like, you know, it'd been done before, but the sort of version of tropical curves they use in the paper generalizes this by replacing the positive real numbers here by an arbitrary commutative monoid. So I guess if I follow the conventions of the previous talk, all monoids are commutative. So we're going to replace R by a monoid, and then make basically the same definition. Except again, it's not quite the same, unfortunately. So let me give you the definition of an abstract tropical curve, and then I'll discuss the ways in which it does and doesn't generalize these metric graphs that we've seen. So again, if M is a commutative monoid, then a tropical curve metrized by M consists of a quadruple, so it's going to be a set and a bunch of functions on this set. So we're going to have R, I, and L. So where? So G is just a set. So we think of this as a collection of vertices and oriented edges, as before. R from G to itself is partially defined idempotent. So the way to think about R is on oriented edges, it takes an oriented edge to its starting point. And on vertices, it's the identity. So the partially defined bit means that somehow not every edge has a starting point. So we allow edges that don't have like a finishing or an end point. So somehow the relationship with what was going on previously is we've kind of just thrown out our vertices at infinity, and we're allowing edges going to them just to not have a vertex at that end. So this is the kind of start point.
So,
Yeah.
this is maybe a silly question, but why the insistence on writing a graph as the set which is the union of vertices and edges, and not a pair v, E as it's usually done? And
I don't
makes
know.
these kind of things a lot cleaner, right?
I think
Contraction's better.
yeah, it works with contractions better. Yes, exactly.
Okay.
I think that's
Yeah.
where it belongs.
Yeah, that's a good point.
So yeah, so this is somehow the start point of an edge, and so if we're thinking of a vertex as an edge of length 0, then like its start point is itself. So this is vertices plus edges. Okay, so the third bit is the I is exactly the same one as we had before, so these edges are really appearing in pairs, and I takes an edge to like the same edge with the opposite orientation. So it's an involution.
And what does it do with a vertex?
Keep them fixed. So yeah, it's the identity on vertices and takes the edge to the opposite one. And then finally, L is like the length function of an edge or a vertex. So kind of vertices are going to have length 0, but edges are going to have some other length.
And that cannot be infinity, the other length.
No, yes. So this is one of the ways it differs from the previous one in that I just couldn't make satisfactory. I'll return to this in a minute. Okay, so there's a few compatibilities. I think actually there's only two. So first of all, that an edge is its own start point if and only if it's equal to the edge going in the opposite direction, if and only if it has length 0. So, like, what we're thinking of, this is if and only if it's a vertex. So this condition cuts out the vertices.
So in particular, so they don't say this on paper, but I guess they mean that R is always defined if L of x equals 0?
It follows from the only way to interpret this.
Yeah. I wish they said yeah.
But yes, like it would be helpful if that was spelled out more explicitly. Okay, yeah. So this is somehow the condition cutting out the vertices, and then secondly, that the length of an edge going in the opposite direction should be the same as the original length. Okay. So this differs from the previous definition in two kind of key ways. Actually, before I say this, I'm just actually going to formalize what I mean by oriented edges and vertices. So the vertices are just the elements of G of length 0. The oriented edges, the oriented edges are the things of non-zero length. These are called in the paper flags. So these are oriented edges correspond to L of x non-zero, so the things of non-zero length. And then they use the term edges for a pair of opposite oriented flags. So yes, this is possibly a bit confusing given the way I've talked about this so far, but I'll try to stick to this from now on, because this is what they use in the paper. Okay. Yeah, so like I said, there's a couple of differences between this and the, if you stick in m to be r greater than or equal to 0, you don't recover the previous definition, unfortunately. So the two main differences are that we've just forgotten about infinite vertices altogether, and we're just happy with edges that don't have an end or a start point. So the sort of thing we might get is something like this, where kind of this edge doesn't have a start point, this edge doesn't have an end point. So if we're thinking about what it means for this function to be partially defined, this function is going to be defined on everything except this flag here, because it doesn't have a starting point. And just to kind of confuse things even more, the ways these are drawn in the paper is by putting an unfilled circle where the sort of non-existent vertices are.
Can you just formally add in an infinite vertex for every R?
Yeah.
So
it's kind of this. It's essentially the same thing. Yeah.
But you also allow multiple edges, right? In this definition.
Yes. Yeah. Because somehow the edges come. We're thinking of this pair as a single edge, and then you could have.
You could have many pairs between. Yeah.
So I could also have another distinct edge from this vertex to itself. Yeah. That's allowed. Okay, so the fact that we've lost infinite vertices isn't a major difference. The major difference is that lengths always have to be finite in this definition. So for all flags, so note that every sorry.
So maybe a stupid question, but couldn't we take a monoid to include infinity?
It's probably not a monoid anymore, right?
Why not?
Why not?
What?
You can just formally, but the edges are still having finite length, so you. Yeah.
I mean,
Oh,
so
oh,
it could be
you
fine.
could, right?
Yeah.
Is it? Let's say if you just formally join infinity, is this still going to be a monoid?
I'd say so.
I think so.
It's pretty associative.
Yeah, oh, yeah, because monoids don't need to have as. Yeah.
Yeah.
Okay, right.
Be hard if in the monoid.
yeah. Okay, so.
But still, we don't have a condition that the half edges that don't have starting points should be infinite. So
Right.
We should
yeah,
all
yeah,
have the
yeah.
same value, or
Yeah.
Yeah, okay.
Because you're going to turn it up.
So I'm kind of So we are always assuming that the lengths are in the monoid, but yeah, whether you're right, you probably can make this work to encompass the previous definition. So what I was going to explain next was actually kind of like why you can still produce things with finite length coming from the pictures we saw earlier. But this was something I was very, very unsure about, so it's probably best not to stick my neck out on that one as to why